Okay, so in this video we're going to be continuing with double integration problems, and in this case we're going to be given the following integral. So we're meant to find the double integral of this function with respect to the region D, and the region D is drawn here, so it's basically a triangular area that is bounded by this function y equals to 1 minus x. So as I mentioned at the end of last video, basically when we're given y as a function of x, we need to include this as our limits. So if we want to write the limits for this integration, we have to start with y. So basically, what is the lowest value that we have of y? Well, y is just going to be constant at 0, so that's going to be our lower bound. And then for our upper bound, basically what you do is you try to see how much y is changing. So you can see that for any value, as you increase x, you basically get blocked here on the upper bound by that function. So that has to be your upper bound for y. And then for x, because it's your independent variable, what you're going to do is you're going to use the limits. So basically those 2 points there that denote the boundaries for x. So that's going to be 0 and 1. Now the way you want to set this up is to have anything that is a function, so that has limits that are a function of a variable, to have it inside. And you want to have any constant boundaries on the outside integral, so that once you evaluate this thing, you get a number out of it rather than a function of a variable. So the way we can set this up is as follows. We're going to have the integral from 0 to 1 and the integral from 0 to 1 minus x. And now we're going to have our function. So I'm just going to take the constant outside. So just as with regular integrals, any constant that we have, we can take them outside of the whole integral. And then we're going to have the function xy. Now remember, dA is your element of area, so dA is just going to be dx times dy. But you need to rearrange this accordingly to the way in which you're integrating. Remember, in this way, we're setting it up such that we integrate with respect to y first. That's why we have these 2 limits here. So that means that dy has to be the element that goes inside, and then dx. So now that we have this, we can begin to perform the integration. So we're going to have the following. This function with respect to y, that's just going to be xy squared over 2. So that's going to be 1 minus x, 0, and then dx. So now we're going to take this down, and that's going to become the following: 0, 1, x times 1 minus x squared dx. So let's expand this out. So that's going to give us integral from 0 to 1 times x times 1 minus 2x plus x squared dx. And then this is going to become 0, 1, x minus 2x squared plus x cubed dx equals to 2. Now we're going to integrate this function with respect to s, so that's going to be x squared over 2 minus 2x cubed over 3 plus x to the power 4 over 4 from 0 to 1. And now once we input these values, we're going to get the following. So that's going to be 2 times 1 over 2 minus 2 over 3 plus 1 over 4. And then basically that's going to be, hang on a minute, am I missing something? Oh yes, I forgot, I canceled this out with that one, so we shouldn't have that 2 here. So I skipped that step. So basically cancel out that 2, and then you're left with this. So then in the end you're going to get the following value, that's 1 over 12. So that's going to be the value of your double integral within that region D. Now there are some cases in which it might be convenient to change the boundaries, so to change the order of integration, and that's the example that we're going to consider now. So let's have the following problem. Let's say you want to integrate the following function given these boundaries: e to the x squared dx dy. Now, what is the first problem you notice with this function? Well, it is a function of a single variable, but you're integrating with respect to x first. And as we know, e to the x squared is not an elemental integral. It's not one that you can just get out of standard results. So how do you go about integrating this whole thing? Well, obviously it would be convenient if we could actually change the order of integration such that we can integrate it with respect to y instead, since we could treat this as a constant. So the first thing we need to do is we need to draw the region of integration just to get an idea of what the transformation is going to look like. So we're going to get the following. Actually, if you notice, we're integrating with respect to x first. So that means that we should actually plot x as a function of y. So that's going to make things easier for us if we start by plotting x on the vertical axis and y on the horizontal axis. So let's start with x. We have the function 3, so that's x equals to 3. So that's just a horizontal line at the point 3. And then we're going to have 3y is the lower boundary. So 3y is just going to be a function with gradient 3. So that's a linear function, which means that it's going to be crossing the x-axis at the point y equals to 1. So this is going to be a region D of integration. So this is the function 3y. Now what we want to do is we're going to take this graph and we're going to exchange the x and y axis. So basically we're just going to flip this around by doing some sort of 180-degree rotation about some imaginary axis that is halfway between x and y, and such that we end up with the following graph. So this is going to be y here and this is going to be x. So obviously you need to make sure that this is a linear transformation. So every point here is going to be projected here. So basically what we have here is we have the line x equals to 3 going here. So that means that we're going to have the line x equals to 3 going here. And then this line 3 of y, we need to take the inverse of that. So if we have x equals to 3y, then the inverse function is going to be y equals 1 over 3x. So basically what we're going to have is we're going to have this line, which is going to have a height of 1 at this point here. And then the line now is going to be represented by the function 1 over 3x, 0. So the one thing that you can notice from this process is that all we did was flip this around. But now notice that the limits of integration have changed, because now we need to define y as going from 0 to this straight line 1 over 3x, or simply x over 3. And now x is just going to be the independent variable, which means that the limits are going to be 0 and 3. So these limits are very different from what we have here. So let's see, obviously performing this means that we're going to integrate with respect to y first. So let's rewrite the integral as 0 to 3. Now we're going to have 0 x over 3 of e to the power of x squared times dy dx. So that means that we can actually integrate this function, because now we treat x as a constant and we integrate with respect to y. So that's going to give us the following. We're going to get y times e to the power of x squared, x over 3 and 0. And now we're just going to put the value of x over 3 into y. So that means that we're going to get the following, 0 over 3. So 0 to 3 of, and we're going to have this constant outside, so 1 over 3 x e to the power of x squared dx. So what do you notice about this integral? Well, we're back to the problem in the beginning, where we need to integrate with this with respect to x. But now we have this. We have this, and if you have done some integration by substitution before, you would know that we can actually perform the following substitution. Let's call a variable u equals to x squared, and then du is going to be 2x dx. And that means that by putting a 2 in here and multiplying this by 2, so that becomes 1 over 6, we're going to get the following integral. So 0 to 3 e to the u. So this, you should make this explicit. This is going to be x du. And then this is going to be the same as e to the power of x squared from 0 to 3. So 1 over 6 e to the power of 9 minus 1. So this is going to be the exact value of that integral. And you notice that the way we perform this integration was by simply flipping this graph around. And we can do this kind of thing for any simple region like this. Now, obviously, we can extend this concept to regions that have something like this. So let's say we have our xy plane. And let's say we have some sort of area that is now bound by two curves. So let's say we have something like this. and then these two curves intercept at some point there, and then this is our region of integration. Then in that case, so let's call this y1 and y2. In that case, y is going to go from the function y2 to the function y1. So each of these is going to be a function of x. So we will not need to write the limits like that. And x, it would be still be treated as an independent variable. So it would go from 0 to some point x naught where they intersect. And this here idea is extended to a lot of different cases. So if you have encountered some difficulty with a function, you can try and change the order of integration by first looking at the domain of the region of integration, flipping it over, taking the inverse of the functions so that you can change the domain of integration, the limits of integration on each variable, and then seeing if actually integrating that function with respect to the other variable first can actually reduce it to a function that you can integrate using standard methods. And in the next video, we're going to see a little bit more of applications of this by implementing the Jacobian to perform a double integration by changing the coordinates of integration in a problem.